In the last two examples of stream pipelines, I used map and sorted. It's kind of hard not to use these in many cases. Much of what you want to do in a stream processing pipeline is to filter, transform and sort. The map function is both simple and powerful. It can turn one stream into another kind, and since we can use as many map operations as we want, we could do a lot with this one operation. It can be as complex or simple as you want it to be as well. The peek method is aptly named because it's commonly used to print elements in interim operations, so you can get an understanding of what is really happening. Of course, you're not limited to just printing output. This operation is susceptible to intentional or unintentional side effects. Finally, there's the sorted operation. We've covered sorted a lot with collections, and this operation is similarly structured to the sort method on implemented collections. You can use it without specifying an argument for elements that implement the comparable interface. If you want a different kind of sort, or the elements in your stream don't implement comparable, you'd pass a comparator. The sorted method gets complicated when you use parallel streams, but I'll cover those complexities in the concurrency section of the course. I'll use the project Streams Intermediate and the main class from the last video. I want to examine the map operation in a little more detail. First though, I'm going to create a seat record for the examples I'll be using in this video. You may remember in previous videos I created collections of theatre seats. I want to do something similar to demonstrate some of the stream operations. I'll create a new Java class, a record in dev.lpa, and just call that seat. It will have the fields row marker, seat number, and a price of the seat. Row marker will be a letter, seat number will be an int, and price will be a double. I'll generate a custom constructor, and for that I just want the first two fields, row marker and seat number. I'll change this code. First I want to insert a new line after the seat number, after the comma before the 0. Next I'll replace 0 with a ternary operator to set up a pricing rule for seats. All seats will be $75, but I'll have the outer seats, seats 1 and 2, and seats 9 and 10 be discounted after row C. I'll check that row marker is greater than a literal C character. I'll use a conditional and next check the seat number values. That's it for the constructor. Next I want a toString method, and I'll generate that. Selecting none for fields. I'm going to return a formatted string. The seat number will be in the format of B001, for example, so I'll print the row marker with a character specifier. That'll be followed by the seat number with an integer specifier with a width of 3, but I want leading 0, so I make that 03. Finally, the price has a float identifier. I'll ignore any decimal value when this is printed, so I make that .0f. Okay, that's a pretty simple record. This pricing mechanism is a bit flawed, since my seat numbers may not always be from 1 to 10 under some circumstances, but it's good enough for this test. Getting back to the main class and the main method. I'll first print a new line. I'll set max seats to 100 and seats in row to 10. I'm going to create a stream variable using var as the type for simplicity. I'll use stream.iterate starting with 0. I want to generate numbers up to the max seats value, which I made 100. The third parameter is a function lambda, and it just increments by 1. These parameters kind of remind you of a traditional for loop, don't they? Here I'm going to return new instances of the seat record, and instead of using generate, I'm doing this with iterate indicating how many seats I want. Then I'm going to use map to return a new seat record. I can figure out the row's character by using the integer on the stream and dividing that by the seats in this row. For example, I divided by seats in row will be 0 for the first 10 sets, so they'll be in row A. It'll be 1 from the next 10 seats, so they'll all be B, and so on. Next I need the seat number. I don't want to use the stream's integer value because each seat number is numbered from 1 to, in this case, 10. Again, I can figure this out with a simple math equation. I can use the modulus of I with seats in row and add 1. When I is 0 or 10 or 20, the seat number is 1, the first seat in the row. When I is 9 or 19, the modulus returns 9, and adding 1 makes this 10, which is the last seat in the row. Finally, I'll print these records out. Okay, so I purposely wanted my terminal operation as a separate statement. This lets me demonstrate a couple of things using IntelliJ's inlay hints. You can see my local stream variable's type has been inferred to be a stream of seat there. In the code I'm showing you here, I start out with a stream of integers, which then becomes a stream of theatre seats. If I run this, I can see all my seats printed. Most of the seats are priced at $75, but after row C, you can start seeing discount seats, the seats that have a seat number of 001 or 002, as well as those that are 009 or 010. Now I'll do another map and put that after the first one in this pipeline. I'll remove the closing semicolon. I'll add another map operation and return a method reference seat : toString. This will return a string. IntelliJ has an inlay hint now after the first map operation, which tells me that at that point my stream had seat elements in it. However, the first inlay hint always shows me the final stream type. Also notice that after the iterate method, it's showing me that I started with a stream of integer. I'll change this map to return a stream of the prices, so I'll just change toString to simply price. IntelliJ tells me the result is a stream of double or double wrapper instances. In addition to streams that take any type, I've already demonstrated that Java has primitive streams for ints, doubles and longs. I can switch to these in a pipeline that started out as a stream. To do this, I can use specialized map functions, and I'll show you this next. In this case, I want to use an operation called map to double rather than map. Now look at the resulting stream type. It's not a stream of double, but a new stream type, a double stream. This is a special stream that handles primitive doubles. It can be a lot more efficient to process a large number of doubles with this type of stream rather than incur the overhead or additional memory required when operating on a double wrapper. I'll add another map operation. First, I'll again remove the last semicolon. Now I'll include an additional map operation. This time I want the price, but as a formatted string. I'll have a formatted float specifier allowing for 2 decimals and use the formatted method. I can do this with a method reference too. When using stream pipelines, oftentimes the method references are easier to read to get a gist of what is happening. IntelliJ is flagging this map operation as an error. Hovering over that, I get the message bad return type in method reference. Cannot convert java.lang.string to double. When you use a double stream, all your map operations have to return a double. To map to something other than a double, I'll have to use another specialty map operation called map to obj. I'll replace that last map operation with map to obj. The stream inlay hint shows the resulting stream is now a stream again with a string type. Let's pause here a minute to look at a slide. In addition to the generic stream that lets you stream any reference type, Java has 3 primitive streams. These are double stream, int stream, and long stream. To change to a primitive stream, you choose a corresponding map to operation as shown in the second column on this slide. To switch to a double stream, you'd use map to double. Map to int will result in using an int stream, and long stream comes from map to long. To switch back to a generically typed stream, you use map to obj. Alternately, you can use boxed. I will show you that next. I'll add a boxed operation before the last map to obj operation. Now I have an error on map to obj, and because I used boxed above it, I can simply make that map here. I will switch map to obj back to map. The primitive streams have many of the same operations, but do include a few extra terminal operations specific to their numeric types. I'll cover these in the next video. I think the sorted operation is pretty self-explanatory, but let me comment out some of these extra map operations and I'll give that a quick test. I'll add sorted after the map. When I run this, I get an exception, and that's because my record doesn't implement comparable. I can simply pass a comparator here, so I'll do that. I want to first sort by the lowest seat price and then the seat numbers string. I'll use comparator's convenience methods to build this, so I'll start with comparing, passing that the method reference for seat price. I'll chain the then comparing method to that. For that method, I want to pass the method reference for the toString method. Running that code. I get my lowest price seats listed first, D001, D002, D009, and so on. Lastly, I want to finish up this video with a quick look at peak. Peak takes a consumer, and therefore its purpose is not to have any side effects on stream members, In fact, the Java docs state that peek mainly exists to support debugging to see elements as they flow past a certain point in a pipeline. First, I'll comment out the last statement, meaning the for each statement. I'll use peek, but for this example, I just want to do it on a limited set, so I'll skip the first 5 and limit the output to just 10, and now I'll include peek, printing out each generated record. Running this code, I don't get any output at all. This is a reminder that peek is still an intermediate operation too, and because of lazy streams, it won't process until I include a terminal operation. I'll uncomment that last line of code in this method, running this again. I can see the output from the peek operation, which includes the arrow. You wouldn't probably use peek in a stream pipeline if your terminal operation is a for each with a println like this. There are terminal operations that aggregate data and give you a single result, and peek is often valuable in those circumstances to try to understand the stream pipeline process. Okay, so this video covered the most commonly used intermediate stream operations. There are a couple of others, but I'll come back to those after I review terminal operations. In the next video, I'll cover these. You've seen for each, but there are many others, so I'll see you in that next video.